hope that from this you can get a sort of a better impression on what actually is involved in this thermodynamic description. So this is one slide from yesterday, where we write a surface energy balance. Just maybe a comment. This term here, I refer to it as RS, the absorption of solar radiation. It includes already the effect of albedo. Then we have the down-related non-wave radiation, the emission, and the turbulent heat fluxes. But because for formulating a heat engine, you need to have temperature differences, we also need to consider actually the energy balance at the top of the atmosphere. This is sort of where the radiation is, or the heat, where the cooling occurs, and where radiation is emitted to space, and the entropy of that flux also plays a role. And we will see some variations, the mean application of this, but also variations. So what happens, for example, when we have atmospheric advection, what happens during the diurnal cycle, and also what happens with what actually sets the diurnal temperature range. This is sort of more recent work that our former student Sarosh has done. And some implications for example, for water vapor pressure deficit or relative humidity, as well as some applications to climate change. And please, if you have any questions, just raise your hand, and happy to stop. So just to quickly just to illustrate what the physics is behind this Carnot limit, it uses the first and second law. And when we use this power plant as an example for how this Carnot limit is being derived, well, we have a heat flux that comes in at a certain temperature. So it's not just the heat fluxes that play a role, but it's also the temperature at which this occurs, because that sets the entropy fluxes. And so we need to have the heat fluxes in, heat fluxes out, and the power generated. So this is the conservation of energy. The first law, heat in is equal to heat out plus the electricity generated. And then we have something that is not so known in climatology. It's the entropy budget. Yeah, so we also have an entropy budget. That means we balance entropy fluxes as well as what the processes produce entropy within the system. It's like, when you had yesterday we had the example of the hot cup of tea in a room. When it cools down and the temperatures become more equal, then entropy is being produced, or entropy increases. And so this entropy budget is in this form, so that we know how much entropy enters the system, because we can take the heat flux in and divide it by the temperature. That's an entropy flux. It's similar to this expression by Clausius, delta Q over T. We have an entropy flux that leaves the system at a colder temperature, and then we have some entropy that is being produced inside the system. And the second law requires that this sigma here can only be greater or equal to 0, so it cannot become negative. And that's the difference to a normal budget equation. When you have advection, or when you have atmospheric mass balances, you can have divergence or convergence. Now, when you deal with entropy, entropy can only increase or stay the same. And then one can take the ideal case where the sigma is equal to 0, and then we want to know what the G is, we want to know what the power is, and then we have two equations, we can solve for it, and then we get this Carnot limit from it. So in other words, that when we assume that there's no entropy production inside the system, then the best case is heat flux times temperature difference divided by a temperature. And this one here being known as an efficiency. So this one can then apply to the land surface. And there I also want to just quickly show you what kind of ingredients go into this, and what the important trade-off or the interactions are. So we have here, we start with this Carnot limit. If we want to apply it, we need to recognize that when we cool the surface by turbulent fluxes more strongly, the surface temperature cools down. And so for that, we need the surface energy budget to know what the surface temperature how it reacts to turbulent fluxes. We can simplify this by linearization, then the expressions become simpler. We can then get a expression for surface temperature from the surface energy budget, can put it in here, and can maximize and get a relatively simple expression that is that the turbulent fluxes are roughly absorbed solar radiation divided by 2. There's a little bit of variation due to the to long wave radiation. And then this is something that I already showed you yesterday. So when you apply this, this is what Sarosh's work, when you apply this across regions with radiation data sets from satellite, maximize power, you can simultaneously derive heat fluxes and temperatures. And I want to show you one application where we can use this. And because, now we can we have the surface energy budget, we have this no limit of the heat engine. And as we go across regions, we can actually figure out why temperatures, for example, become warmer in the deserts. Yeah, and I'm someone, I did my PhD on routing depth and land-atmosphere interactions with a climate model, and I always thought of how important the biosphere is. And the answer to this question I found a little bit disillusioning, but that sometimes that's how science works out. So let's look at that, because we can have many reasons, but at least maybe two of the most prominent reasons why, or hypotheses why deserts are warmer on average, is on the one hand because you have water limitation. So you have less water, so you can't cool by evaporation. Or is it because deserts are often more sunny? Yeah, they have less clouds. And what I showed here on the x-axis is what's called the aridity index. It's a very common classification in hydrology based on Budiko's work. The aridity index is defined by potential evaporation, so that's the theoretical ability to evaporate off the surface if there is sufficient water divided by precipitation. And so you see, as you go into more arid regions, so here, when you look at this axis here, there you have that the land surface could evaporate a lot more than it receives precipitation, so it is water limited. You see that, there is strongly more water limitation, but there are also less clouds. And when you have less clouds, you have more heating by solar radiation. And now, to sort of understand what came out of this study here from Sarosh that was published in 23, we also need to recognize, how arid regions actually form. And I think you're probably well familiar with it. And that has to do with that, you have the Halley circulation, where you have a surplus of water in the tropics, then you have this descending air masses in the subtropics. And associated with that is heat transport that you have from the equator to the subtropics. And then you have the standing air motion and so on. And so what we found, so we have heat advection into the arid regions. And to understand what happens to the heat engine, I have this illustration. So when you have heat advection by the atmosphere, so you get heat from the tropics and it's transferred to the subtropics, it heats our heat engine at the wrong side. Yeah, it's the cold side that becomes warmer because of heat advection. And what this does is that it actually changes this efficiency of the heat engine. So your temperature trade-off changes and it shifts that maximum power limit to a lower heat flux. It alters this trade-off between the heat flux and the temperatures. And this is something that I show you in a minute. This is what we found in observations that we were able to reproduce with this approach. So, so when we look at the variation of how heat fluxes change with aridity, we see that here on the one hand side, the dark line is series, and the dotted line is what you get from maximum power. So we see that overall the turbulent heat fluxes are reduced as you go from humid to arid regions. And of course, evaporation decreases. This is the blue. But the sensible heat flux to some extent compensates for it. Yeah? So if you have less evaporation, you get more sensible heat flux, and that balances the lack of water to some extent. And here we see sort of this temperature difference between the surface and the radiative temperature. So we see that it is reduced as you go into more arid regions because of the heat advection in the subtropics. And so with this, we can actually reproduce that increase in temperature. So this is again from another series data set. So when we go from humid to arid, we see that, roughly there's an increase by about 12 degrees. So and the subtropics are on average about 12 degrees warmer than sort of humid regions. And we can then try to explain this temperature difference by looking at, the deviations in the energy budget of the surface. So how much of this temperature difference is due to a difference in solar radiation? How much is it due to a difference in downwelling long-wave radiation? And how much is it due to the change in turbulent heat fluxes? And then we divide by this linearization constant, and then one can actually reproduce or calculate this. So we see that heat fluxes, for instance, they reduce by 40 watts per square meter, while solar radiation increases by 40 watts per square meter. Downwelling long wave doesn't really change. And so we can put this in here. So we have total about 80 watts per square meter change, increase. Then we need to divide by this linearization constant. It's about 5 or 6, I think. And then we get about 14 degree Kelvin warmer, which is, well, quite close to this. And of course, this is not as precise as if you would use a climate model or ERA5 and so on. But what I like, coming from physics, is that one can relatively easily estimate this change and see what are the causes for it. Yeah, I mean, we see it's this increase in solar radiation. Well, it's because there are less clouds in the deserts. So we can summarize this by saying that deserts are warmer because, well, on the one hand side, they receive more solar radiation, and the other is that it's a weaker power plant, so the turbulent heat fluxes are suppressed. Yes? In principle, very good point. I mean, in principle, yeah, I mean, you can actually look at what happens in global warming, right? I mean, this is the delta RLD that would increase. And actually, I think tomorrow we have some talks, or I want to talk about this because a lot of the downwelling long-wave radiation actually depends on the atmospheric window, which also depends on clouds. And so, yes, deserts actually warm more strongly with global warming, but less because of this, but simply because of the atmospheric window. Yeah. And so maybe we can also talk about that later or tomorrow about that. Yeah. Okay. So now I want to get sort of more specifically about changes during the diurnal cycle on land. So the diurnal temperature range and also another modification of this heat engine picture. And I start with a really simple question, that why does land actually heat up more strongly than the sea? And when you look at textbooks, or the usual answer I get for this is because of the heat capacity of the ocean, right? Only partially. Because the most important difference between the ocean and land is that water is transparent. And because it is transparent, solar radiation penetrates the surface ocean, reaches 20, 30, 40 meters deep into the water, and is absorbed. And then, you have all this depth, and so you have a large heat storage. Yeah, so it's the combination of water being transparent plus a large heat capacity. When you go to land, well, dirt is not transparent. So the solar radiation is all absorbed at the surface. Yeah. And I think what I want to emphasize, it's this difference in optical property. Yeah. And it has a very big manifestation, because when you heat the surface, when all the solar radiation is absorbed at the surface, it is heated quite strongly and you get buoyancy. And that's sort of when you get this heat engine working, right? Because then you have a temperature difference forming. But then, during the day and the night, you have a vast difference in solar radiation, right? I mean, during the day, you have up to 800 or 4,000 watts per square meter coming in, heating the surface. And then at night, you don't have any solar radiation. So what happens with all that heat? Yeah, in the ocean, it's clear. I mean, it's sort of, the ocean buffers it. It's the heat storage of the surface ocean that is buffering it. And over land, this huge imbalance in solar heating and absence of solar heating, that's buffered by the atmosphere. Yeah, that's the lower part of the atmosphere. You can call it convective boundary layer, that is providing that heat storage to balance out day and night. And so I have that sort of drawn up here in a little cartoon. So this way. Yeah, so we have a huge surplus of heating during the day, but the cooling occurs day and night. Yeah, the cooling by long wave radiation. Long wave radiation doesn't know a night; it just keeps going all the time. And so you have a huge surplus, and land and ocean differ because this surplus for the ocean is stored below the surface, while on land it is actually stored above the surface. And when you store heat above the surface, you store it inside the heat engine. Yeah, and so, yeah, because I mean, we talked about, the surface is heated and then there's somehow it cools into space. But now we have another term. We have this heat storage change in the atmosphere, and that actually also modifies the entropy budget, because when you have a change in heat content, remember delta Q over T is an entropy term. That actually took us years to figure out that this was the problem we had in reproducing these diurnal variations. So we needed another term in our entropy budget. And just to show you how strongly this makes the energy balance different between land and ocean, I show you here some observations. This is here from a tall tower where our institute is involved with. It's in the middle of the Amazon rainforest. It's called Atto. And this is from a colleague down the hallway from my office. He shared some data. This is the mean energy balance during the day for January 2018. You can see solar radiation here in red. And you see that the latent and sensible heat flux, they follow very closely solar radiation. Yeah, so they track the heating of the surface. While long wave net radiation, you see it doesn't really change much during day and night. Then there's also an eddy covariance site over Lake Erie. So that's not quite the ocean, but it's a lake, a big lake in the US. And what you see there is, for 1 month, in June 2014, strong solar radiation, but the turbulent heat fluxes, they average out. They don't show this pronounced diurnal pattern. Yeah, so a very different energy balance, because the water buffers the whole thing, and the turbulent fluxes are much more variable depending on wind speed, and so they don't depend on the solar radiation directly. Yeah. And so we are focusing on this now. So the land surface buffers this strong surplus during the day, the heating during the day, above the surface. That affects the heat engine. It leads to a diurnal temperature range. And we'll show some work that is not quite submitted, but I find really exciting, because it shows that the vapor pressure deficit and relative humidity are very closely related to the diurnal temperature range. And then also the last part is that it actually also leads to a greater climate sensitivity. Okay, so why is this so? Because you have another entropy change, which is related to the heat storage change. And what it does is that the way you can imagine it, the surface heats the lower atmosphere, and some of that heat input does not go into generating work and acceleration, but it simply heats the atmosphere. And that's why we actually called it a cold heat engine, because it's like, in the morning when the sun rises, the atmosphere is still cool, and you need to warm it up during the day, and that is your heat storage change, but you also perform work at the same time. And that affects this trade-off again. So basically, it shows you that heat flux, you need to sort of remove that heat storage change from the heat flux. When you then maximize power, what you get is that you get a stronger flux, a higher flux, so it actually has important implications for the diurnal variation of that heat engine. And just to show you here, these are two observation sites. One is from Israel, which is a very dry pine forest. The other one is from tropical Brazil, a rainforest site. And maybe just look at this right side. So here are the observed turbulent fluxes. Here is the one predicted by maximum power. The light blue are the one without considering the storage effect. The dark blue ones are the ones with storage effect. So you can see that the turbulent fluxes are actually enhanced because of this diurnal variation. And here over the rainforest, it also works really well. And you can see here, this is site E and F. We had 4 other sites that I don't show you. It was Alaska and something in Germany, and I forgot what the last site was. Sarosh actually also looked at this across FluxNet sites, and also there found that the agreement is really quite well, as well. I mean, here in the scatter plot, as well as sort of the diurnal cause. And so, in other words, we can sort of distinguish, or we recognize the difference between ocean and land surfaces, because on land, these heat storage variations by the sun are stored in the lower atmosphere. And that changes the thermodynamic limit and the outcome of this maximum power limit. That works actually really well, and it produces higher turbulent fluxes on land compared to ocean. Okay, so now we want to take this to related to the diurnal temperature range. So we've already seen, sun goes up and the atmosphere heats up. One example or one weather station I usually use to just play around and identify certain patterns is a site from Jena. Jena has this is sort of where I work, where our institute is. There is a weather station that has been operational for a long time. I think routine measurements since 1821. And not quite so long, I think, from the 1880s. They also have minimum and maximum temperature during the day. So, and more recently, actually at the top of our institute, they also measure it half hourly, and so you can actually, or 10-minute time step. So you can see this variation during the day, where you have the coldest temperatures. This is here in summer, and in summer in Germany, the sun rises before 6, so it's more like 4. So you see here the lowest temperature around sunrise, and the maximum temperature sometime in the late afternoon. And so this is here the diurnal temperature range. Also, minimum, maximum temperatures are shown here. And what you can also see here is that actually with global warming, you see here sort of a time period in this more paler colors. This here was the minimum temperature in the period from 1961 to 1990. So you can see that the minimum temperatures actually have increased more than the maximum temperatures. And I want to get to that as well. So when we go back to the energy balance, so what's actually happening? What shapes this diurnal temperature range? And well, quite simple, solar radiation, right? I mean, solar radiation heats the lower atmosphere. Well, not quite so simple. So solar radiation is absorbed at the surface, and then you have surface emission, you have the sensible heat flux, and you have the latent heat flux. Now, the latent heat flux is evaporation, and it doesn't heat the atmosphere. It only heats it once it condenses, right? So that's why it's latent. Yeah. So in other words, it is only the emission as well as the sensible heat flux that heat the atmosphere. And so when we can already form a hypothesis that, so when we have water limitation, we actually have a stronger heating. So we should have a greater diurnal temperature range in the presence of water stress. So Roche combined our maximum power limit with the partitioning in sensible latent heat, and so he got an expression for the diurnal temperature range. Let's say here is heat capacity and the typical height. Here is the equilibrium evaporative fraction, and here is net long wave radiation. And so we can see that the main influences of the diurnal temperature range are solar radiation and evaporation. When we compared it to FluxNet or RL5, we saw that the correspondence is actually quite nice, high correlation. And then we can also identify that when we have less clouds, we have a greater diurnal temperature range, and also when there is less water, we have a greater diurnal temperature range, and can also put proportions on, how important is water stress for shaping the diurnal temperature range. So that was published last year, and we are still playing around with this. We're trying things out. I mean, our hope is that we can actually use this equation and actually infer water stress from observations. Yeah, maybe we can use if we know what solar radiation is and we know the diurnal temperature range, and the diurnal temperature range is something that is very well observed. Maybe we can use observations of diurnal temperature range to infer water stress. So the diurnal temperature range reflects mostly the heating by solar radiation, but it also has also water limitation plays a certain role. Very recent work, we looked at the vapor pressure deficit or the relative humidity of air, which is also something that is routinely measured. And there we figured out that actually there is a very simple way that it can be explained also in very simple terms of translating the diurnal temperature range into the vapor pressure deficit or relative humidity. Which is, we basically multiply the diurnal temperature range with the slope of the saturation vapor pressure curve. Yeah, and the idea is quite simple. When you think about, I'm not sure how familiar you are with VPD. I mean, this is sort of hydrologists and ecologists. They prefer VPD. Relative humidity is probably something that you're more familiar with. Relative humidity is water vapor divided by saturation water vapor, right? Now, what happens when the atmosphere heats during the day? Well, you have a bit of evaporation, but the residence time for water vapor is 10 days. So the evaporation during the day won't change EA by much. But the heating of the day changes your saturation vapor pressure. And so, in other words, as the day proceeds, your air becomes drier because you're heated without, yeah? So that's the dominant factor that's shaping the relative humidity changes during the day. Yeah. Okay. So now, then I thought I would also like to show you some applications that one can use this framework to look at temperature extremes. We have, we have two examples where we looked at this. On the one hand side, it's just in general interesting to look at the service energy budget and see which terms in the energy budget are actually the ones that result in high temperatures. Yeah. The soil heat flux, we ignore it. Yeah, you can, sorry, yes, that's a good point. We don't consider the soil heat flux. hang on, 22. I just want to go back. I think we ignored the soil heat flux. I mean, it's usually quite small. I mean, it's, it only penetrates for about 5 centimeters or so. And if you take forested sites, there you usually don't have a soil heat flux.
Right? That's why I was asking at which scale you are considering, which temporal scale. At half-hourly scale, it still can be steady. At daily scale or more, it probably should be zero. That's what it's.
Well, at the diurnal temperature range, that's of course defined on the whole daily scale. And in principle, if the soil heat flux would be large, you would expect a smaller diurnal temperature range, right? Because you would have a soil, you would also have a diurnal temperature range in the soil, right? So you have also a heat storage change in the soil. Does that make sense?
What I'm trying to say, if you are ignoring soil heat flux at temporal agglomerations more than daily, then it makes sense because overall it will be averaged out. If you're trying to see the effect of the net energy budget on the TDR, then probably it makes sense to include it, right? Because that also will change with season and different times, and also depending on the soil texture and soil properties basically.
Well, I mean, so far we have mostly ignored it, and it's not, our estimates are not that bad. I mean, maybe we could improve them if you can include the soil.
Okay. So what I'm trying to say, let's say you have the same formulation, this
Yes.
equation on the previous slide, basically on the this equation.
Yes.
So if you apply it over a desert soil and then a soil over a forested region, so probably that will make.
Yeah, I mean, I think when I think about it, I mean, I think there may not be many fluxnet sites over deserts, right? I don't know. Does anyone know?
I do have one.
You do have one, okay. And yeah, I mean, they're probably the ground heat flux. I mean, I think the rule of thumb is 10% of net radiation, right? So yeah, I mean, so that would mean that we the diurnal temperature range should be reduced, I guess, right? But when you have a greater heat flux. Yeah.
Then my another query was, if you go to slide number 17, I guess.
Yeah, this one.
Storage heat flux here. That remains open.
The atmospheric heat storage.
Yeah.
Yeah, I think I took that slide out. The thing is, there's also a really simple way to do that. And if you have instantaneous solar radiation, yeah, and otherwise, at night you have zero, and you can take the diurnal average of solar radiation, and that's like this. Actually, it's here. We can use this diagram here. Yeah? So you have an instantaneous solar radiation that varies during the day, and you have an average solar radiation. When you average it, this is what needs to be removed so that you reach a steady state over a longer time period. Is that your solar heating is equal to the loss, and the loss is just the average of the solar radiation. Yeah, so it's
the dynamics, aerodynamic conductance changes and all.
All of this is without aerodynamic conductance, right? And we actually hope to infer aerodynamic conductance from this approach. But we are not quite there yet. We just don't have enough time, I think, because we already know how we want to approach it. But I think this is sort of a great, I'm actually quite curious to see how well it works. Because the aerodynamic conductance, this is sort of to parameterize turbulent heat fluxes. I think another way, when you are sort of more coming from the climate modeling community, it's the drag coefficient that is related to that. And
certification, basically.
Yes. And I think we will be able to. We have a surface energy balance that is constrained with turbulent heat fluxes, so we can infer surface temperature. With this heat storage change in the atmosphere, we can reproduce the diurnal temperature range of air temperature. And so we know what the difference is between surface and air temperature. And we also know what the turbulent fluxes are. And so that should help us to infer the aerodynamic conductance. Yeah, and then we will see how it compares with sort of semi-empirical equations.
an inverse approach. Yeah.
Yeah.
Thank you.
Yeah, sure. Yeah, good questions. Yeah. If others have questions, or don't understand something, you just raise your hand. Thank you. So we were extreme temperatures. Yeah. So one can also look at temperature extremes and heat waves and so on, and look at which terms of the energy budget actually change. And this is first what Chinese visiting student did regarding temperature extremes over Tibet. And it looks a little bit complicated, this diagram, but let's go through this. I mean, so she looked at what are the 10% of the warmest maximum temperatures and what are the 10% minimum temperatures, and how are the deviations in the surface energy budget for these times. And I think I can cut the story relatively quickly because it was quite clear. So the maximum temperatures were extremely warm when there was an anomaly in solar radiation, which is somewhere here. And the nighttime temperatures were extreme when downwelling long-wave radiation was greater than average. And so, and then one can look at what causes these changes in downwelling long-wave radiation. One can decompose it into sort of an emissivity and cloud cover. And it was actually both. It was sort of water vapor anomalies and cloud cover anomalies. And I think what it actually shows is, the interpretation that we basically gave was that these extreme temperatures, either hot extremes or cold extremes, they were actually related to synoptic conditions. And these synoptic conditions were particularly those that advected either clouds or not clouds, right? So it's about whether the atmosphere changes the solar forcing or the greenhouse forcing, depending on whether you look at nighttime extremes or daytime extremes. And so this was actually not involving maximum power or anything. It was just an analysis of the surface energy budget. But actually, Sarosh has also been interested. I mean, he also worked together with Yinglin on temperature extremes and maximum temperatures. And well, what I showed you is that one can reproduce average temperatures well with the maximum power. We can also infer the diurnal temperature range based on maximum power and this heat storage change in the atmosphere. And so when we take the average temperature and add half of UTR, we have a simple estimate for the maximum temperature. And there again, Sarosh compared that to observations and finds that it reproduces here one observational data set, CPC, and also this plot shows the comparison of CPC to our estimate and the comparison of CPTC to RR5. What he wants to show is that our comparison is just as good as RR5. The root mean square error is actually a little bit reduced. The R squared is about the same. And so it seems to capture the majority of the maximum temperatures, the driving factors that shape maximum temperatures, and that then relates to how the radiative fluxes change at the surface. But now I want to sort of show another application where we use this approach to look at the differences in global warming. It's sort of quite well known that land warms more strongly than ocean surfaces. And so a few years back, we actually used this approach also to understand why that is the case. And this is here from a IPCC AR6. So when you look at the global warming by 2 Kelvin, you see that land generally warms more strongly than ocean, and also that the deserts warm more strongly than humid regions, what we discussed earlier on. And so the question is, why does land warm more strongly? And it's about 50% more stronger than the oceans. And we can also see this in time records here. This is the NASA GISS data set. The blue is ocean, black is global, orange is land, and you see that land warms more strongly than the ocean. Well, if we look at energy balances again, then, remember we have these turbulent fluxes that only occur during the day, but not at night. While over the oceans, you have much more smoother behavior. Quite sure why I'm showing that one. Here you don't have any turbulent fluxes. You actually have so we used to cooperate with a site in Russia. Now, since the Ukrainian war, there are no collaborations with Russian scientists anymore, unfortunately. But I think this is really interesting data, because you can also look at the surface energy budget in the winter, in the polar winter. It's really, really cold. It's a -38. You see that there is no real diurnal cycle. Of course not, no solar radiation. And so the reason why it is not even colder is because you still have about 150 watts per square meter of downwelling long-wave radiation that actually keeps the temperature determines the temperature of the surface. So in other words, when we look at the energy balance at night or polar nights, then it's only downwelling long-wave radiation that matters. While during the day, we have the heating by solar radiation, but we have also the additional cooling by the turbulent heat fluxes. So we have two forms to cool during the day, and during the nighttime, we only have the emission. And because of this, we have our heat engine that cools the surface only operating during the day, but during the night you don't. And the maximum power, the outcome of that maximum power limit is such that it actually results in cooling by about reducing the temperature to about 1/2. And so what you have is that the night times would warm twice as much as during the day when you have global warming. And while over the ocean, because the surface ocean buffers the solar forcing and the turbulent heat fluxes operate day and night, you have the same warming day and night. And so that actually then means, because the daytime length is about half of 24 hours, you have 50% more warming on land than you have over the sea. And when you look at different climate models, here's sort of a whole suite of CMIP5 simulations. This ratio of 1.5 applies to practically all models, maybe even higher. That may be due to Arctic amplification. But the 1.5 line is a pretty good lower estimate for this difference in warming. Yeah, so it would fit quite well to this explanation. Yeah, and then that's right. So Sarosh also revisited this warming using his expression for the diurnal temperature range. So it is also well established that this stronger warming during the night than during the day with global warming would reduce the diurnal temperature range. In fact, this is also something that I didn't say that here, but these are again our observations from Jena, where you can see that when you compare two 30-year periods, the night times have warmed by 2 Kelvin, while the day only by 1.3. So there is this stronger warming during the night. And so the diurnal temperature range actually decreases. Here we express this as an optical depth. Like this is like a ratio between downwelling long-wave radiation to outgoing long-wave radiation at the top of the atmosphere. And so this is more global warming. And we see how the diurnal temperature range decreases in with our estimate with RL5 and with FluxNet. when you translate that to global warming, so when we have here 2 degrees warming, for instance, then you would expect that the diurnal temperature range on average decreases by about 0.5 Kelvin. And you can see here that CMIP6 ensemble, some data set and so on, they fit quite well to these estimates. Yeah, so it seems like a nice way to understand why the diurnal temperature range decreases and how it is related to global warming. And also that one can estimate and understand these phenomena with relatively simple physics of heat storage changes and how that affects your turbulent heat fluxes and what makes land different to an ocean surface. So stronger warming of land is caused because of the stronger warming during the night. Yeah, so it's the night times that cause that basically there's amplified warming on land. And that's the stronger warming of nights because there is no turbulent cooling during that period. Now I want to sort of in the last part, I want to sort of briefly talk about the application to Germany. So a regional application of our approach, and I want to show you that one can use this approach to attribute why Germany has actually warmed disproportionately more. I mean, maybe you care more about India. So just take it as an example for how one can use this kind of surface energy balance approach to understand why certain things happen. So what we did first, I showed this graph here before. There's a data set from NASA GISS, ocean warming time series, global warming, land warming, and the red line that wasn't labeled before are surface temperatures from Germany. You can see that Germany has, especially since 1990, has warmed quite a bit more. And the question, of course, is, why? Is the greenhouse effect especially relevant because, I don't know, something special in Germany or something, So we can take an energy balance approach. So maybe to just show you this to illustrate what that actually means. So here we see here, now we are in 2025, so we are somewhere around here. So you see that we have already received about 1.5 or 2 degrees warming in Germany on average. And to just show you what it means, so when we look at maximum temperatures, again, in summer, my favorite station in Jena, you see this is here the climatological reference period from 1961 to 1990. And you see that the observations here, the frequency of measurements here, this is the sort of the step line, fits actually quite well to sort of a Gaussian distribution. When we looked at what happened during 30 years, so we took the next 30 years, we see that the mean warming on 1.6 degree, that's sort of consistent with this global average that I showed a moment ago. And we also see that, the extremely hot days, for instance, doubled basically in frequency simply because that frequency distribution has shifted to warmer temperatures. Now we can estimate temperatures in Germany again by a surface energy balance approach using maps for Germany. Maybe it goes great. And what I actually used is a data set from the German Weather Service, which is based on weather stations. And weather stations, they don't observe energy balance components. They usually observe minimum temperature, maximum temperature, relative humidity, and in case of Germany, they also have a measurement of global radiation. So there's incoming solar radiation they have as well. And they use that to make actually gridded data sets of it. But again, this is not energy balance components. So part of the problem was, how do we reconstruct the surface energy balance? Now, one thing is that we have tested in my group an empirical parameterization, semi-empirical parameterization for downwarding normal radiation that one can infer from weather station data. Actually, Saurabh will talk a bit more about that. That actually worked quite well. The surface energy balance components in terms of the heating by solar radiation, the downwelling long-wave radiation, the emission of the surface, and the turbulent heat fluxes. And one thing when you look down here, what strikes is, what I find striking is that actually similar or sort of equivalently with the increase in the greenhouse effect was an increase in solar radiation. Yeah? So by the same magnitude. So when you look at the end of here 2020, we have about that the downwelling long-wave radiation has increased by about 10 watts per square meter, and solar radiation has also increased by 10 watts per square meter. And that was actually attributed by other groups in Europe. There was sort of a period in the 90s when the aerosols have reduced. But since the 2000s, it seems like there's actually a nice paper by a colleague from Leipzig, Johannes Kraas. They showed that actually daytime cloud cover has reduced. And that sort of is consistent with this increase in solar radiation. Yeah, so the strong warming that we see is only half of it is due to the enhanced greenhouse effect. The other half is due to an increase in solar radiation, which may also be related to global warming, because maybe the lifetime of clouds has reduced. Now, it has a really important implication, and that is, when you have more energy available at the surface because of more solar radiation, you have more turbulent heat fluxes. When you have more turbulent heat fluxes, you have also more potential evaporation. Yeah? And actually, potential evaporation has increased quite a bit also in the last 30 years. And so when you look at the difference between precipitation and potential evaporation, this is sort of measure for water surplus or dryness. And when you look at the trend of the last 30 years, you can see that Germany has actually gotten quite a bit drier over the last 30 years. And maybe I can just sort of add sort of as an anecdote. I mean, the whole reason why I got into this is that in Germany, populists claim that wind turbines cause dryness, and which I find is ridiculous, because dryness is caused, for evaporation, you need energy, and energy comes from sunlight and not from, the wind speeds play only a marginal role. And so I wanted to actually then say, okay, but it's actually a good question. Did actually Germany get drier or not? And so I went into these estimates, and I was really surprised to see by how much drier it actually got over the years. So maybe just to give you a proportion, you only see here deviations. You see that precipitation is highly variable. It's because we are in the mid-latitudes. Mean rainfall is about 700 millimeters per year. And potential evaporation has increased by 100 millimeters a year. So it's quite a significant increase in potential evaporation. Okay. And yeah, you can also make maps. So, this is a map of how the solar radiation has increased. This is the downwelling long-wave radiation. And again, you see that they are similar magnitude. Okay. And so with this, I want to finish this part, and then in a minute hand over to Saurabh. So what we've seen is, and I think this is sort of an important insight that I gained from this, is that, especially in meteorology, you often think about how important the atmospheric dynamics are. And I think what this application of the maximum power limit shows that, solar radiation is still the most important forcing of the land surface, right? Of course, it's modulated by whether clouds are there or not. But from that, we can actually infer a lot of things. We can infer the mean temperatures and the temperature range. We saw that the VPD is tightly connected to it. We also saw that the heat storage variations in the atmosphere, they affect this thermodynamic limit. And they also enhance this climate sensitivity because you don't have these turbulent fluxes at night. And I'm sure of this application to regional climate change. And so I hope what you get from this is that, like another approach of how one can do climate science and with relatively simple approaches or concepts, and that one can also, of course, relate to climate models, climate sensitivities and observations. And so I think now I want to hand over. I mean, maybe we take brief questions before we move to, I mean, if there are questions, otherwise we can also have discussion after. So, oh yeah, of course, we can make a break for tea, and then after, and then yeah. So we have then okay. So we go for a tea break, and then we have two talks afterwards. Saurabh, I mean, basically, what he talks about is how maximum power can be applied to the vertical, to how the temperature variations along elevation, and then you talk about cool stuff with GPS on atmospheric water vapor. Yes. So, are there any questions? I mean, otherwise we can also just. Oh yeah, there's a question. Maybe we should take a few questions, then we go into coffee.
You showed that 35 slide in that you showed an equation delta T land approximately 1.5 delta T ocean. So is it like global or does it varies in tropics, extratropics and all?
You know, that's a yeah. I mean, hang on. So I'm trying. Um, yeah, I mean, there are regional variations. Yeah, for example, you know, when you look at this map, you see that you know, the humid tropics don't warm as much as the deserts, for instance. Yeah. So it is a continental average over a maritime average, or compared to an ocean average. When also in the ocean, you know, you see, for example, this blob here, which is probably a reduction in sea ice that causes quite a strong warming. But then when you average it out over these vast regions here in the tropical ocean, then it doesn't show up much in the global average. Or not the global average, the maritime, or however you want to call it, ocean average. Yeah. Actually, speaking of which, I find that actually interesting that you know, despite these regional variations, it seems like this 1.5 line is pretty robust across these climate modes, which you know seems may raise some interesting questions. I don't know if there's something to find out.
No question how will break for
Hello everyone, I'm Saurabh. Hope you all are energized after the tea, after having the tea. So a little bit about me. I am doing my PhD under Excel at Max Planck Institute, and I will be briefly talking about uh, how we can understand altitudinal temperature variations using the surface energy balance approach. So for first question, why is it even important to understand? So from the theoretical standpoint, understanding surface temperature along elevation would give us a sense how water and energy is partitioned at the land atmosphere interface. But from the more practical standpoint, it can be very helpful while downscaling the surface temperatures, for especially for the complex terrains in the mountains. And secondly, we would also like to understand under what conditions the climate sensitivity might be enhanced. So there has been studies which show that the higher elevation regions are warming at a faster rate, and we would like to understand the reasons behind this elevation dependent warming signal. But before that, why does the temperatures even decrease with elevation? So the common first answer which comes to our mind is it's just atmospheric lapse rate, but it is not really the case because when we look at the temperatures along an atmospheric column, it is primarily an adiabatic process. So we know that the air parcel near the surface, it gets heated up, it becomes buoyant, and it rises upwards. So it expands at the cost of internal energy, and this expansion happens with no heat exchange with the surrounding. While if we go along the surface, it's a diabatic heating and cooling going on. So the dq is non-zero for this process. So we can get very different rates along the surface and along the free atmosphere. Uh, but we can now go into more depth what this surface heating and cooling is all about. So I will briefly refresh about the surface energy balance. Maybe Axel has already talked about it in great detail, but maybe it is helpful for someone to just look at the notations again. So we have a surface, and the solar radiation is absorbed at the surface. So the surface and the surface temperature, the surface heats up and gets some temperature. Let's say it is Ts, and then it emits as per the Stephen-Boltzmann law. It is here we refer it as RL up, and then the atmospheric column absorbs and re-emits back to the surface, hence heating it up. We call it RLT, and the surface also has the water on it, so it can evaporate, and this constitutes the latent heat energy flux. We call it Le. And also, air above the surface can warm up. It causes buoyancy. So here we refer it as sensible heat flux. Together, they constitute the convection, and like Excel talk about how this convection is constrained in the Earth system. So looking at the constraints in this Earth system, so first important constraint is at the top of the atmosphere, where net solar incoming radiation is equal to net outgoing plus minus a heat transport term. On the surface, okay, on the surface, the heat energy balance is closed. Uh, so we can have the heating terms together and cooling and equate them together. But rather non-trivial constraint is comes from the heat engine model, which constrains the power output of this heat engine. I would not go in detail, and because Excel already told you about that. Yeah, so maybe I will quickly skip. Okay, so we come back to our question: why does surface temperatures decrease with elevation? So on the left, I have shown this surface temperature profile from the era 5, and the red color box plot show that the reproduced temperatures from the maximum power limit. So we can see that the maximum power limit can very well reproduce the surface temperature along the elevation profile. And second, the second thing which is important is that it is the downwelling long wave radiation which decreases along the elevation, and not really the net solar absorbed radiation or the turbulent heat exchange. So the question comes, why does RLT decreases then? And the reason is because at lower elevation, the water vapor content is higher. So it leads to higher emissivity, and hence the RLT is higher at the lower elevation, and not at the lower elevation, and not this is not the case at the higher elevation. So we could get a sense that maybe it is indirectly it is linked to water vapor, and lapse rates are also linked to water vapor. So there exists an indirect link, but it is not the one-to-one correspondence. But again, rather interesting thing is, why does then RS not change as much with the elevation? So we looked into this a bit, and on the right side, you could see the albedo effect. I mean, it is the function of the atmospheric transmissivity and the surface properties, which is the albedo effect. So there exists some compensating effect between the two. So we can expect that the RS, I mean, this can explain that why RS doesn't change as much as we go higher in elevation. But then why does RLD doesn't change with elevation that much? So, I mean, this can be reduced from the maximum power limit. So I think Excel has already shown this calculation that it GOPT scales as half of absorbed solar radiation. But I mean, maybe I would point out a different way to look at surface energy balance, that the net solar heating of the surface is partitioned into net cooling by the long wave radiation and through the turbulent heat exchange. So there is some sort of competition between RL net and J, and RS remains constant. And this competition, I mean this partitioning, is decided by the maximum power limit, which comes out to be roughly half of net solar radiation. So that's why we can expect the why turbulent heat exchange doesn't change as much. Again, so using the surface energy balance and some parameterization, I will briefly talk about it. So this is, I mean, RLD can be represented as emissivity times sigma T raised to the power 4. And this is rather non-trivial because temperature here is the 2-meter air temperature. But we know that the atmosphere emits at different, it is a layered system, it emits from different layers, but we can really use 2-meter air temperatures. And for emissivity, we can, I mean, I will come to that. For emissivity, we can use the 2-meter water vapor pressure. So this is non-trivial. And so one could look at it as like the temperature is the proxy for the atmospheric heat storage, whereas the water vapor at 2-meter is basically how much of water is there in the column above it. So it is the precipitable water. So or the absorptive mass above the column. So I mean we can get an expression. I mean, just by doing some rearrangements, we can get an expression for RLD, which is RS minus J opt. And before I showed that the RS minus J opt part of the surface energy balance doesn't change as much, but it is the emissivity which changes. So there is a function of emissivity epsilon upon 1 minus epsilon, which changes along the elevation, and this really causes the RLD to change with elevation. So once we have that, we can invert that relationship to get these near surface temperature profiles. So the part which is governed by emissivity, it decreases along the elevation, and this is the constant term which we get from the maximum power limit. So one can also take the derivative of this to relate the temperature profiles to the emissivity drop along the elevation. And then one can also get the emissivity drop from the parameterizations, because there are relationships between emissivity and water vapor from Broodset and Crawford and Duchamp. We will come to that. And one can establish an analytical expression between dTs by dz and dTA by dz and show how they relate to each other. Okay, so this is just the summary of method and approach. So we started with thermodynamic constraints and surface energy balance. We looked at the modified form, I would call it a modified formulation of RLD, and then one could derive an analytical expression which relates surface temperature profile and the lapse rate. And okay, yeah, this is the lapse rate. And then one can directly link the temperatures to the atmospheric emissivity. So just to refresh your mind and refresh the memory, and these are the data sets we are using currently. So we use ERA5 pre-analysis data, this series, and there is one. These are the baseline surface radiation network. This is maintained by Meteoswiss, and these are basically the radiation measurements at a very high these are very high temporal radiation measurements. These are at 1 minute resolution. We can really average it out and get some good estimates of uh, surface energy balance, especially at higher altitudes. So coming to how well it performs. So on the left, I have plotted the RLD from era 5 and RLD from the modified formulation. So it seems that it performs really well. And on the right, I have compared the temperature, the skin temperatures from the era, or the 2 meter, I think it is 2 meter air temperatures from the era 5 and the temperatures from the modified RLD formulation. So I will talk a little bit about how how these parameterizations look. So yeah, so Brutzer give this formulation. So there is a power law relationship between the emissivity and vapor pressure. So it is very sensitive to vapor pressure. There is a EA term in the denominator, but since the values for temperature are like 288 plus minus 10 won't make that difference. So it is much more sensitive to EA than to temperature. So it is primarily a relationship between emissivity and water vapor. So in his paper in 1975, he gave basically two relationships. One, this one, and another which was, it was converted to only EA. Relationship of emissivity only to EA. Yes, TA is ambient temperatures, but if you just take the log and differentiate it, so you will find out that emissivity is much more like sensitive. Yes. So here in this paper, it was 2 meter air temperatures which Brutzer used. Thank you for the question. So these are, but one thing is that these are clear sky emissivities and not really the all sky emissivities. So one could get a estimate for all sky emissivity. So this is FC is the cloud area fraction here. So one could get that by dividing the RS by potential solar. Dividing the solar radiation on the surface by the potential solar radiation, so one could get the estimate for FC. And so when for the cloud fraction term, like this part of emissivity, the emissivity is basically 1. So you can imagine it as Fc into 1 plus 1 minus Fc into clear sky. So this formulation is called basically the Crawford induction. And just to Yinglin, a postdoc in Axel's group, was previous visiting PhD student in Axel's group. She worked on this and reproduced the RLD. This is the RLD from series. This is from era 5, and this is from Crawford induced parameterization. So you can see that it works really well. And she estimated the clear sky RLD for the FluxNet sites and just compared it with the observations, and it turned out to be working really well for the FluxNet or for the series or for the era 5. So just showing that these parameterizations are very robust and work really well. One important thing which can be done is you can also decompose this R&D relationship into part which is governed by emissivity and part which is governed by the temperature variation. But or I would reformulate it. A part which is governed by the absorptive mass and the part which is governed by the atmospheric heat storage. So you can really decompose it into these parts. And if you are interested, yeah. So this is one application. I'm deviating a bit, but if you are interested, you can look at it at this paper. You can see how well the deviations, these are the diurnal deviations plotted at the hourly scale. And you could see that the most of the deviation is contributed by the atmospheric heat storage term, or the atmospheric heat storage part of IIT. So I just put it up here. If you're interested, you can have a look. So coming back to how does RLD varies with vapor pressure and what it implies for the sensitivity of RLD to higher elevations. So on the left, I have plotted the water vapor pressure with elevation, so it decreases with elevation. And on the right, I have shown the RLD variation with the actual vapor pressure uh, from uh, from the VSR in sites. I mean, these are observations, and from the Crawford and Duchamp parameterization. So one can see that at the lower vapor pressure, the RLD increases. I mean, it is more sensitive at the lower vapor pressure, which corresponds to the higher elevation regions. And at the higher vapor pressure, it is much less sensitive because the plot, it is a nonlinear relationship and it is much flatter there. So this has some important implications to climate sensitivity with elevation. And tomorrow, I won't go into the climate sensitivity part because tomorrow Axel will be talking about it. So it relates to atmospheric window and how it relates to atmospheric window. But for the teaser, I have included this plot where on the x-axis I have plotted the mean EA values for RFI, and on the y I have the rate at which the clear sky RLD is changing, and these rates were calculated over the period 1940 to 2025. So you could see that for lower vapor pressure, the RLD has changed much more compared to the higher vapor pressure. So this is the trend with respect to the mean vapor pressure profiles. So with that, I would like to conclude. So, first part is that maximum power principle works really well to reduce temperature along the elevation. And second, it is the downwelling long wave radiation, it is also the dominant energy balance component, and it is the primarily the RLD decreases with elevation, which drives the temperature decrease along the surface, uh, along the elevation, and temperature decrease can be directly linked to atmospheric emissivity. And we can also establish an analytical expression which connects the dTs by dz by atmospheric lab states. And we are working on downscaling surface and or near surface temperatures in complex mountainous terrains. And I would be really interested to have some discussion around this, or if you have some ideas around this. And also we are currently investigating the elevation dependent warming and how it is connected to the atmospheric window and so on. So thanks a lot. If you have questions, you can ask, and you can also write to me on. Thank you very much. Shukla. Vapor pressure versus height, right? Right there. So what I just wondering is, suppose we are at tropical. And,
That issue. The vapor pressure actually is sorry, the actual amount of water vapor is less. So do we expect that suppose at a 5,000 meter elevation, there is more chance of getting a snow line there than at the tropics? So no, I mean, I want to see this curve as a function of latitude also. So latitude versus height and contours of vapor pressure. So have you checked how does that look like?
So vapor pressure. It is at higher latitudes, so vapor pressure is lower. So that is a fact. But so one could I mean, there are two effects. One is elevation and one is latitude. Temperature decreases along the latitude primarily because there is less solar radiation. But if you constrain the latitude, if you are talking about a latitudinal band, then RS is maybe not changing that much. It is primarily the RLD which is changing. So
because I have not seen any much of curve which says RLD as a function of latitude also. So I
think there was one. Yeah. I mean, this is. I think here maybe you could see RLD. I mean, it decreases as you go towards the higher latitudes.
Maybe I can just add to this. I think the thing is that way, I think you can plot it. The latitude is not because I mean, this for these parameterizations, the senior parameterizations, you can actually use directly output from error 5. Low wave downward magnification divided by sigma t to the power. The emissivity, you can see how well it corresponds to water vapor. Yeah, and so I mean I think you can. So the variations with latitude are entirely by indirectly just by a temperature. Then you have the variation.
Can you show that graph? Last graph. Last one. And this one. This graph, elevation versus vapor pressure. This is the global data or this is some station data?
I think this is I think tropical. This is I think the tropical or the mid latitudes. I mean I divided data set into the latitudinal bands, and this is for the illustration purpose. So the relationship, yes, for the but the decreasing relationship would remain the same.
General, tropics is already having less vapor pressure, less. So then, in that case, this graph can be much lower. That is 5,000 or something. That is his question.
Okay, so I mean, why this doesn't go beyond 4,000 meter or something?
In extratropic, sorry, in mid latitude, because here it's in tropic itself, it is going here. So in mid latitude, where already water vapor is less, so there it may go much higher level.
Yeah. Of course. Yes. Yeah. Absolutely.
No question, then thank you, Dr. Saurabh. Now I will request Dr. Vijay. Dr. Vijay. Just one announcement is there. Today afternoon there is no lecture is there. Tomorrow we are having full day lecture. Today afternoon there is some interaction with some people. So today after lunch there is no lecture.
Yes. What's this? Yeah. Use this only. This for laser.
Yeah. The topic I'm going to cover is how are we going to measure 3D water vapor field and soil moisture from geodesy. From yesterday and today, you might have already heard that lot of water vapor variations in the model. Dr. Krishnan was mentioning that when it is a high resolution model, not like Clausius Clapeyron equation for 1 degree Celsius, but it turns into rain. But in the same thing, as a low resolution model, there will be a higher amount of water vapor. Similarly, Dr. Rajivan was giving many things about soil moisture. But the question is, how are we going to measure it? And I need not explain the limitations of water vapor measurements. Conventionally, you all from the atmospheric science field, you know. But what I would like to add here is how geodesy can help you not only on the space from the ground measurements, how we can get high temporal, low cost, and all weather measurements of water vapor as well as soil moisture. So basically, as a geodesist, I'm a geodesist. Not our focus is not mainly on atmospheric science. We will be working on tectonics and other aspects of that. But all these atmospheric parameters is a noise for geodesists. But there is potentially all these noises can be inverted into signals. So that will be very helpful for all the atmospheric and earth system monitoring. So that's what I just wanted to show you the possibilities and what is the theory behind it of inverting these noises into signals here. Many may not be very familiar with what is geodesy, which has happened all over the world. So I would like to mention what geodesy is. The community is also very small and it is picking up in India. It's a very ancient science that's the mother of many of the scientific field. So as per Merriam Dictionary, a branch of applied mathematics concerned with the determination of the size and shape of the earth and the exact position of a point on its surface and with the description of variations of its gravity field. But there is a revised definition now. Geodesy is the science of accurately measuring and understanding three fundamental properties of the earth: its geometric shape, its orientation in space, and its gravity field, particularly the changes of these properties with time. So that gives the geodesy into the thing. And what you are seeing on the left is the gravity field of the earth, not like what we always take it in our models like perfect sphere. It is not so. So all these parameters is affecting all the things starting from sea level change and whatever you are associating with in the climate science. So all those things geodesists are working on, how to what is the exact figure of the earth and things like that. So this is an interdisciplinary science covering almost many fields. So starting from mathematics, computer science, physics, and all, and many in the present applications, it is used for mapping and surveying. But it has applications on atmospheric science, astronomy to space science, everything. So this connects almost all branches of the science. This is a very classical subject, as I said, when the man started measuring the land in the BC. At that time onwards, geodesy started. Now the modern geodetic systems, after the era of the satellites, there are many satellite-based geodetic systems, starting from lunar laser ranging, satellite laser ranging, and before satellite era, VLBI, that is called Very Long Baseline Interferometry. They use quasars to find out. Basically, what is important is the clock pulses to find out the shape and orientation. And the navigation satellites provided a great advantage on that. So we all know that in our mobile phones, we are using GPS. So GPS is one of the main thing. That is what I'm going to talk today about, how we are going to use GPS. So other than GPS for gravity measurements, we are using gravity recovery satellites that's called GRACE. And SAR, now present NASA and ISRO, NISAR has thrown up, and the data is also open. That is being applied on many fields, particularly on soil moisture. Other products can be derived. Ultimately, you all know that. So this talk will be on GNSS, that is Global Navigation Satellite System. Why we are saying instead of GPS as GNSS, similar to GPS, there are many other navigation satellite systems. GPS is owned by US. So similarly, GLONASS is the one owned by Russia, Beidou by China, and Galileo by European Union. So all these are global navigation satellite systems. In addition to that, there are regional navigation systems called QZZ, that is Japanese quasi satellite system. And India do have IRNSS, or popularly called NAVIC. We do have our own regional navigation systems. So all these navigation satellite systems are used for geodesy, navigation, and mapping purposes. I need not emphasize the importance and uses of GPS, because it has become part and parcel of everyday life for our regularly taking all our mobile and locations and all the services. But the thing is, I'll just tell what GPS is and why these error sources and inverting into signals are important. So let us take an example of GPS. So GPS will be having this, for example, 6 orbital planes. In each orbital plane, theoretically 4 satellites. So 24 satellites is required. But right now, even as a spare satellites, everything together, around 31 is available. So similarly, all systems together, all the GNSS systems, 100 plus satellites are flying. So what is there in the satellite? So this satellite is nothing but they are having an atomic clock. A very precise atomic clocks, rubidium and cesium clocks are there. So that provides the signals in multiple frequencies. Typically in 2 frequencies in the case of, now it is 3 frequencies in the case of GPS. One is L1, that is basically these are all L-band observations. L1 is 1.2 gigahertz and another is 1.57, so roughly 1.6 gigahertz. So these 2 signals will be coded with the satellite's information. We'll call a pseudo-random noise code, PRN. This is the same principle of how our mobile works on the GSM data, that is same microwave frequency, but it is all coded with, because we need to identify which satellite is sending the message. So what message it gives is, it gives the message of its position and the clock correction and other navigational messages. So it basically says that this is the time I'm sending it, and at this position I'm sending this time, in a colloquial language. So why that is important? To get the position, generally GPS position, what we are having in our mobile phones, latitude, longitude, how it connects is, we know that there is a satellite here and this is the receiver here. And once if we know the distance of it, we can find out the range between this XY of Z, but this will be an unknown actually. So once if we know the distance and things, we can solve this equation with 4 satellites if time is also unknown. So we will be getting the unknown of the receiver, XYZ of the receiver. That's a simple principle. But it's supposed to have this range, supposed to be a straight line. So then once if we know what is the time of flight of the signal, which leaves the antenna of the satellite and receiving and reaches the receiver, antenna of the receiver. So once if we know the time delay, multiplying into C, the job is very simple. So it's supposed to have the straight line, but in reality, it is not there. There are many error sources. One is the orbit itself. It won't be as predicted. There will be orbital perturbations will be there. So that need to be corrected. Clock, though it is a stable clock, there will be a mild clock errors will be there. And the moment if it enters into ionosphere, the refraction plays the role. The major refraction source comes from the ionosphere. Then the tropospheric refraction. In the tropospheric refraction, the more complex part comes by the water vapor. And instead of directly reaching the signal, it just reflects, it can reflect back and come back, and that is what multipath. So typically the equation has to be like that. This is the range, the geometric range. But this is added by other noises. This is ionospheric component, this is tropospheric component. And if we have 2 frequencies data, we can eliminate, since it is 2 frequencies, ionosphere is a dispersive atmosphere. So the refraction is a function of frequency. So we can use as an advantage of using these multiple frequency signals, same information in 2 frequencies. So we can actually nullify the ionospheric, at least in the first order. Then the remaining will be other biases and troposphere. See, the question is, if we could remove that, then we can reach the higher accuracy. The actual error budget is this. The orbital clock is 2.5 meter. And satellite clock gives 2 meters. Receiver noise is 0.3 meter. And the ionosphere is very high as 5 meter. Troposphere 0.5 meters. And the multipath is 1 meter. So that adds to 11.3 meter in the range. which translates into tens of meters in the positional error. So basically, it won't be really useful for any of our applications. So what we need is we need to bring it to the centimeter level accuracy, where geodesists as we are working on that. So as part of that, we need to remove all these error sources. So as parametrically, we can estimate and remove this tropospheric error, and that can be converted into the water vapor. So the question is how this tropospheric refraction happens, how the water vapor actually causes this refraction. Is it only the water vapor which causes? So the basic physics behind it is, you may be knowing that these water molecules having H2O, we know that. So there is a bend on 104.5 degree in the molecular arrangement. So this asymmetric geometry is a direct consequence of the two lone pairs in oxygen repelling the bonding pairs. Okay, so that gives the electronegativity contrast. For example, oxygen's electronegativity is 3.44, is far more electronegative than hydrogen. That is 2.2. So what happens? This shared electron pulled towards the oxygen. So this gives the del plus here. So that makes the water molecule as a dipole. So that dipole is around 1.85 dBA, which is around 6.17 into 10 to the power of minus 30 coulomb meter. So this is amongst the largest of all common atmospheric molecules. N2 and O2 have zero dipole moment. So this is the specific the physics inside it. When we are applying a electromagnetic field, microwave electromagnetic field on this water vapor, so there will be a torque in that. So this torque, unlike N2 and O2, the polar H2O can interact with gigahertz range electric fields. That is why this L band is getting affected via orientational possibility. So this is the physical origin of its anomalous refractivity. And typically water vapor will give more and liquid water will not give, because the bonding of the molecules will be higher and degrees of freedom will be more in the water vapor. So that affects the L band more. So that actually creates, when the electric field goes this orientation, creates the refractive index of that. So the refractive index will be basically very small. So we will be using a refractivity instead. So that is dimension into 10 to the power of 6. N minus 1 into 10 to the power of 6 that we will use as a refractivity. The Smith-Weintraub expression of this is a constant, and dry air partial pressure divided by temperature and water vapor partial pressure, and then a higher order term. So basically this part is the dry air electronic polarizability, and this gives the water vapor electronic distortion polarizability. This is a smaller wet contribution. This is a dry contribution. And the more important contribution is this is the permanent dipole orientation. So this is what actually it makes the dominant refractivity on that. So if we could estimate that and remove this part, we can get the wet refractivity profile. That is what we will be doing it. This is much more explanation of how the polarization happens and the orientation dipole, how it happens. So I'm just skipping that. So when we are from the satellite to the receiver, instead of the straight path, it bends because of the refraction. So this is, we will call as slant wet delay. So if it is a vertical, that is a zenith delay, but this is a wet delay. So wet delay is 10 to the power of minus 6 integrate. We will integrate along the path. Plus bending. The bending will be very small, so we can neglect over that. And mapping it to the vertical, we will be getting the zenith wet delay. So this will be mapped to the vertical. So we will be getting hydrostatic delay and wet delay. This is how we will use the mapping function to map this zenith wet delay. So what will happen is, so like we will be having a cone of measurements. So from that cone, whatever the ray path goes, all those things will be transferred into the, mapped to verticals, and we will get the zenith delay. So once if we get the zenith net delay of the troposphere, we can model the hydrostatic delay. That is basically a dry air contribution. There is a Sustaminian model and different models are there. So that we can model and remove it. Once if we remove it, what we will be getting is the wet delay. So why we are interested on that for all the applications of navigation and other positioning, modeling and removing the water vapor is highly tough, and we cannot be basically a model and get the accurate data. So instead, as a parametric estimation, while doing this analysis, we will parametrically estimate not only the position, we will be getting the tropospheric delay and tropospheric gradient. So all those things will be parametrically, it will be retrieved. And once if we retrieve that delay, that can be converted into the water vapor. This is a simple transformation term, which is a function of atmospheric mean temperature. So that we can actually convert into the water vapor. So this is how we will be retrieving the water vapor from the GNSS measurements. So basically, this will be a column water vapor. This is the example which we did in 2006. So you can see that this is a water vapor variation which was compared with radio sand observations. A 3-year of comparison of water vapor with radio sand observations. We used different methodologies to derive because getting the mean temperature and the surface temperature was not possible, because originally all these GPS receivers were established for finding the tectonic measurements, how the Indian plate is moving. So that is what the original objective. So there was no automatic weather station or any temperature measurements was with that. So we used at that time INSUP data sets, and we derived it to the closer value, we interpolated to it, and various means of finding the mean temperature we have used. Then finally we compared that with radio sand data. The bias was really it's promising, around minus 0.6935 was the bias, and RMS was 4.5 millimeters. So then we did some experiments on that, how diurnal variations, because this typically we can estimate quite good estimates we can get every hour. And even now the methodology has improved. We can even get every minute to that. Every minute we can get the water vapor over the GNSS antenna. So high temporal resolution we will get. So then we had one station here at Leh and Hanley. So this is the station. So we used that data set to find out how the water vapor varied during the Leh cloudburst event, which happened on 5th August 2010. And you all may be knowing how it happened. Just for a summary, I am providing that. On August 5th, the INSAT IR imagery is actually showing that for every 30 minutes how the cloud pattern actually varies. So cyclonic circulation over lower levels over the western Rajasthan was there. And the convective cloud band extending from southeast to northwest developed over Nepal during the afternoon of 5th August 2010 and moves towards Jammu and Kashmir. So intense convective clouds developed to east of Leh by 2130. And then the rain gauge measurements, but rain gauge measurements, this is so localized event, the rain gauge measurements at the airport didn't pick it up that. So this is the water vapor which we have measured over Leh from estimated from the GPS data. So this is the 4 years of data set. So the blue one is the GPS. This is NSUP data. So the blue one is the GPS one, blue and red dots. So you can see that the maximum water vapor, column water vapor was 25 mm over Leh. This is what the maximum it was. But during that time on 2010, what it happened is there was a prolonged dry spell. After that dry spell, there was a significant increase in the water vapor, which translated into the rain. So there was a signature on that. So on seeing that how it happened here, I have just further improvised. You can see that continuous moisture buildup. This was picked by GPS data. And then this is the TRMM accumulated rainfall that was only available. So there is a moisture buildup and translated into rain. Of course, this is not a single parameter. Other parameters are involved, but I'll just tell you that how useful this information, and this is for every 2 hours. So we measured water vapor for every 2 hours here. And this is during Mumbai cloudburst event on 26th July 2005. We had a data set at that point of time. Here also you can see that a higher moisture buildup, which was captured by the GNSS data set. And this is another example of having it during a Nilam cyclone. We computed the water vapor over Bangalore. So when the cyclone actually approaches the Bangalore, this is the distance between the location of the depression or deep depression to the receiver. So when it reaches Bangalore here, how the moisture field increases and which maps with rainfall. Just these are all the three cases which we used basically to study whether it well captures the moisture variation. But water column, water vapor, only it won't be useful for all of you. But what is needed is a vapor field. So how to convert that vapor field? The one advantage is we can have a tomography of that. Instead of one single receiver, if we have a network of dense receivers, then using the ray path crossing the ray paths, all this we will make it call as a voxel, that is a volume pixel. So in every volume pixel, how many rays crosses that matter. So if we are having a dense network of GNSS receivers, so we can use all the slant wet delay which is crossing into the voxels. Then we can actually make a tomography out of it. From the tomography, we can get the vapor field. Basically, it is a 4D. Because for every sampling time of, say, for example, 1 hour or even 30 minutes, we can get these values. So better will be 2 hours interval. So this is the vertical profiling, and same thing we can get at different time snaps over this area. So that is the idea that we are actually proposing. There is no such work reported from India, and your director was kind enough. So we had a discussion with your director, and we are also planning to make one such a dense network as a proof of concept to find the tomography. So basically, it should not be too sparse. It has to be too dense. So there should be a crossing of the ray path. That is the schematic of that. And on these volume pixels, we will be getting the water vapor moisture field, basically. So this is one example which is from Hong Kong, the study. So they used a 54 by 54 kilometer a network of GNSS receivers. So during different precipitation events and for tomography, different techniques they have used. This basically two different tomographic methodologies, and that was actually compared with radio Sunday. You can see that this is during 4.1 mm, and this is a rainfall of 9.6 mm and 11.4 mm, and this is 4.4 mm and 7.9 mm on different days. So from this, the moisture field and vertical profile was captured, and that was actually compared with radio sand experiment. So this is just one particular example. So similarly, there are many such cases are there, which has been done at few places. So this is the promising one. If we could turn it, this will give the high temporal water vapor field. So other than converting the refractions, which initial slide I have told that reflection also causes error. So this reflection also can be used for sensing the other environmental factors like snow, soil moisture, vegetation, water content, etc. So that we will call as GNSS reflectometry, interferometric reflectometry. So the principle is when you are having a GNSS receiver here, these are all reflected signals. So this supposed to get the signal straight to the antenna, but instead it will be a reflecting one. So we will be using both direct and reflected waves, and we can form an interferometry of that, which eventually will provide the variation in the antenna height. So which is the reflection of which eventually be the path length of this. So that provides how much is the soil moisture or snow accumulation on that. Because of the high dielectric content, there will be a direct one. There will be a small penetration if it is a dry layer of few centimeters. So it can actually penetrate a little bit, and so this is one example by McWright et al. 2014. So they have actually measured from 2006 to 2018 the snow depth variation. So you can see that this is how typically a GNSS antenna look like, and this is connected with the GPS receiver. And this is a dry land, and when the snow comes off, this is supposed to be 2 meter height, and this is the snow coverage. So the reflection actually causes the variation. From there, actually, we can measure the snow depth. That was actually compared with all the conventional measurements, and it is very promising. So this one actually, it shows that the complete reflection zone of that at different elevation angles. This is at low elevation angle, and this is at higher elevation angles. So basically, every day we can get the one measurement. daily measurements. We can temporally also we can go. It depends upon how the algorithms we are using and how the quality of the data. But typically per day we will get the reflections, things. So similarly of soil moisture also we can actually measure it. So this is the example of soil moisture content. It's not from us. This is from Larson et al. 2008. So Larson has worked a lot of things on this reflection and interferometry. So their group actually it showed the promising results of how it can be used for soil moisture. So we are actually initiating a new one with IIT Madras, IISER Pune, University of Kashmir. We are actually establishing a network in Western Himalayas. So basically to find out soil moisture and snow. So in addition to that, the recent studies by Larson in 2020 showed that it's not only soil moisture, even the vegetation water content also can be captured. It is all just how we are going to segregate the signal and we are going to get it. So what is the advantage for us now? So this one left side, what I have shown is the survey of India's, we call as cores, continuously operating reference stations. Basically, these are all GPS receivers, GNSS receivers installed. More than 1,000 plus receivers are available in India. This is for surveying purpose. We will tell us our real-time kinematic survey to get the accurate position. The corrections will be beamed from here, and the corrections in the rovers will be corrected for all the surveying and location-based purposes. So that is the idea. That is why the reference station network has been established. But basically the data set is same. One GNSS data we can use for many purposes like water vapor, soil moisture, snow, vegetation index, and etc. All the parameters. So if we could potentially convert all these things, all these data set, we will be having a very good amount of water vapor field over this region. So there is a huge potential in it. Atmospheric scientists can make use of it, but there is no direct ready-made product is available. But once if we could invert it, all this data, we can actually make it as a useful product. So this is the one which we have actually we have developed as part of our tomography experiment, a simulator, because with this network, this won't be useful for tomography because it's still coarse. So how to make a usable network, a tomographic network, and also we can actually make a synthetic GPS data to find out how well it can capture extreme rainfall events or any other things. So right now we have developed one simulator for that. So we are actually working on that to get the tomography. So this is the potential application which I wanted to show you that how this can be reaped. These informations can be reaped for atmospheric science. Thank you. Yes. Actually, raindrops will not affect. I was expecting that. So there is an information which I put because that's a basic question whether raindrops will affect that. Actually, this is the thing. The molecular state is initially I pointed out that that is bonded well, and for this particular frequency of L band 1.2 and 1.3, liquid water droplets in the clouds are insignificant. So that is why it is prominent to make water vapor.
Yeah, at some point you showed that there is a role of temperature in determining the correction.
Yeah.
There are two steps. I think in the end also temperature is used, but the number n also at some point was determined. I was wondering.
No. This we won't determine. This we won't model that. What we will use is this is the principle behind it.
Yes.
How the refractivity as a function of it. But we will be estimating directly from the delay and we will be converting it.
Yeah. I was wondering.
Of course, we will give this information as an a priori information. That matters how. Yeah.
My doubt is that is your inversion from errors to water vapor sensitive to temperature also? So do you think that?
Yes, but not very sensitive. What will happen is we can use any standard model for the a priori. Remaining goes as a parameter estimation. We will be actually constraining the that is why we will be using the not mobile receivers as a static receivers. So over the period of time, we will be refining the position. So we know both the receiver as well as satellite position. So since that is there, this will be provided as an a priori information. But then over the evaluation of parameter, the best fit will give the actual values. But it do have the matter. So the initial value, initial condition, as good as then the values also will be better. And but this matters. Finally, converting the wet delay into water vapor.
Yeah,
So this is an important parameter.
that's a function of temperature.
That is a function of that is a function of mean temperature. So now right now we are using only empirical relations of the mean temperature to the surface temperature, which may not be whole good for all the regions. So we have actually evaluated for Indian region, but even on the many specific regions we need to use. The other way around is instead of using for it depends upon the application. Instead of inverting it, we can directly take the delay and we can map it with the other parameters so that this can be avoided.
Thank you, sir, for the talk. Is it possible to get water vapor profile from a single receiver without using that tomography?
No, because we will get only along the ray path the integrated column mode, integrated water vapor.
Okay, only
Slant wet delays we will get. For our convenience, we are mapping into the wet delay, but profiles we can't get from the single receiver. So that is why we are planning for a tomographic experiment. So we can use many ray crossings. So from there, we can build a tomography. Yes, yes. Hmm. Yeah, yeah, yeah.
Sir, as you mentioned, the water vapor stacked up in the mid-troposphere. Is there any threshold for identifying the cloud burst based on the stacked up water vapor?
Uh, so far, actually, there are studies which shows the correlation between extreme rainfall and the water vapor buildup. As I mentioned, that this is not the only parameter. So the thermodynamics of the event need to be studied, need to be well understood. So this can give some initial signatures that there is a moisture field, but whether it turns completely into the rain is depends upon the physics and how it uses.
What percentage of this water vapor can be converted into the rain during that cloud burst event? Have you?
I haven't studied, so that we need to know the thermodynamics of the cloud burst.
Thank you.
Thank you very much. Thank you.